will use to actually run that monad model. Delete that line because it's not relevant. And then this is the line that you guys have used to print the results out. And they look something along these lines. They'll look different because we're going to start at a different random starting place in each one. Okay? So far, so good, right? So what we're going to do is we're going to add a second species to these graphs. We're going to keep the parameter, we're going to keep the resource, we're going to have two species and one resource. What that means is what we're going to try to do is we're going to add a second line to this figure, but the phase plane diagram, we're going to have two species and a resource. That would require a three-dimensional phase plane diagram, which can be done, but we're not going to deal with here today. We're going to drop that part out. Okay? You want to go for it, Amos? Go for it. The package RGL will be your friend. You can make three-dimensional graphs in R, it's great, but beyond what we really want to do today. So, this is the function that is used to generate this code. And what I've done is the code for this function I put on a web server. Up until now, I've not asked you to dig into that. But in R, we can see the code that goes into any function just by typing the name of the function here in the console. So I'm going to do that now. And I get out a bunch of code here. I'm going to copy this. I'm going to select it, copy it, and I'm going to get rid of that, do not save that, thank you very much. I'm going to make a new script, I'm going to paste that in. And this function called calcmonadcomp, I'm going to make a new version. I'm going to call it calcmonadcomp Tim. And I'm going to save this new function, give it my new name. Okay? Now in here, there's a couple things that go on. First of all, we figure out what are the equilibrium amounts of resource and the equilibrium amount of the consumer. And these come directly out of the monad model. They come out exactly the same way like we have done in class yesterday and last Monday. What we do here is we determine what are the initial size of the consumer and the initial size of the resource going to be. Remember that when we're solving differential equations, not only do we need the differential equations, but we need to provide initial starting value, because all they express is the change in population size. So we need to tell it where to start. This line then actually projects forward through time what are the population sizes that we are expecting. Finally, this section makes the information for the phase plane diagram. We're not going to be doing that. I'm just going to delete that here now. In fact, in the return, what we return back out to the user, I'm going to get rid of anything that talks about the phase plane. Okay? Now, one layer deeper into the rabbit hole, because this is not sufficient. What this line actually does is it calls a additional function that actually contains the model itself. You noticed here that you don't see the differential equations written out anywhere. So we need to do that now. And that is done in this function called monad model. So again, I'm going to copy that, bring it down here to the console, paste it there, and we can see what is in this function called monad model. And what is in there is this code right here, which again, I'm going to paste into my new script. And again, I'm going to call that monad mod Tim. And I'm going to make this a new function. In R, everybody can make functions. It's a wonderfully democratic language that way. And what you're seeing here is, ignore this line. You don't need to touch that line. What you see here are the differential equations that make up the monad model. If you've got today's lecture or lab handout, you'll recognize these because they're what appear in there. And so what we need to do is we need to have another line for the dynamics of the second consumer. So I'm simply going to copy this and paste that. And I'm going to have consumer 1 and have consumer 2. Now, this ingestion, what is that ingestion? Well, that's actually defined right here on line 16. And that ingestion is how much resource is the consumer consuming. And I want to have a second one of those, one for each consumer. So I'm going to copy that, I'm going to paste that, and have ingestion 1, and have ingestion 2. Now, because these are two different species of consumers, we would expect them to have different parameters explaining their rate of assimilation, growth, etc. So I'm going to do that. Rather than just using a single Umax, I'm going to use Umax 1 and 2, and KU 1 and 2. The lecture handout explains in a bit more detail what these parameters actually mean. Notice that I'm not changing resource, because resource, that actually represents how much of the resource is actually present, and there is only one resource. So it doesn't make any sense to have resource 1 and resource 2. In this model, we're only going to have a single resource. And so now that means that here on lines 17, 18, and 19, I can make that ingestion 1 and ingestion 2. The parameter D represents how fast is the flow through the system. That has nothing to do with the two species themselves. It's simply a parameter of the system, and so we're going to leave that as D. Now, what happens to the dynamics of the resource? Well, this is sort of how the resource flows through the system is what that term represents. And then this represents how does the first consumer use the resource. So what we're going to do is make that consumer 1, and we're going to make simply another statement here saying that consumer 2 is also going to reduce that rate. Finally, this last line, the return, says what information are we going to put back out to the user. Well, we need not only the change in consumer population size for species 1, but we're also going to need that for consumer population size 2. Okay? Francis?
But you need to change the injection in the de-resource things as well, for 1 and 2.
Very good. So here on line 20, yes, I need to make that consumer 1 multiplying by ingestion 1, consumer 2, and ingestion 2. Good catch. If we run this, R puts that into memory, and you can see that changed over here. Our environment now has a new function in it. It's called monad mod tip. Now that's what we're going to use in our modified function here. So we're going to use monad mod tip. And we need to give it a whole new set of parameters, not just Umax, but Umax 1, Umax 2, KU1, KU2. D, as I said, is going to stay the same. R naught is the concentration of material coming into the system, so we're not going to change that either. And honestly, I don't remember what Y is off the top of my head, so I'm not going to screw with that. You may want to screw with that. I don't remember. Now, I'm going to simplify things by actually taking out all of this material. And what that means is that when we run this function, we need to supply initial sizes for it. Okay, so I'm just going to cut that out of there. And that means that here in the return, I'm also going to cut this out because we're not going to be calculating. I'm just simplifying things down substantially. Okay? So we're just going to return this one thing, which are the predictions. And that too, and now we have, should be calc monad comp to Tim. I think it just doesn't show Tim on there, but I think that is actually all the same. Oh, we also need to change this because we need to make sure that all that information, all those parameters are getting in there. So that needs to be Umax 1, Umax 2, KU1, KU2. Okay? So now you do see that you have UMax1, UMax2, etc. So now if we come back over to our original script, this is what you got off of succeed. I'm going to copy this line, I'm going to paste it, and I'm going to say that I don't want to use the original function, but instead I want to use this one. And we're going to use these parameters, UMax1, UMax2, KU1, KU2, D, R0, and Y. And when I run this, it's going to throw an error. It's going to throw a variety of errors. First of them is that I never told it what the initial population sizes should be. And so I'm going to define that now. I'm going to try to define it. Oh dear, what have I done? No, I can't. Oh, there it goes. That was strange. Make sure I actually define this correctly here. What's the initial population size going to be of consumer 1? Well, let's look here what was used in the original model. It's going to be somewhere between 1 and 6. Let's call it 3. Consumer 2. Let's give it something different. Let's give it 2. And let's give resource something else. So it started around 2. Let's make it 1.5 for now. Okay? We get another error. Now, R is very frustrating because it gives you lots of errors. Read the errors. What does it say? UMax1 is not found. Aha! It's because I forgot to define a UMax for the first species and the second species. So I'm going to take this line, copy and paste. I'm going to make UMax1 and I'm going to make UMax2, and I'm going to make them slightly different, just to, for variety. Now, is this going to work?
We need to add KU.
Yeah, we're going to need separate KUs for the two species as well. So KU1, KU2, and again, I'm going to give them different values just, for fun. I want no use having the two different species with the exact same parameters. Now let's see if that will go. UMax2. See, what have I done there? What's that error mean? A misspelling is what that error means. Somewhere in here, I've got
It's on the first
No,
page.
it's the
first one.
In your model comp.
thank you very much. Good catch. All right, so I don't get any errors. Let's see what I get as output. I get a whole lot of output here. I get time up to 500 times steps. You can adjust how many time steps you want. Consumer 1, consumer 2, and resource. Okay? So then we can use that to plot up and make a graph that looks like this one. Let's try doing that. I'm going to use the function matplot, which allows you to make a graph of an entire matrix all at once. What's going to go on the x-axis? It's going to go through this value time. And what's going to be everything else? What's going to be on the y-axis? It's going to be everything else. So that's going to be everything except for column 1. You could do this in other ways that would be more straightforward, but I am lazy, and this is one way to make a quick graph. So what do we have there? We have the dynamics of the first column, second column, and third column. Okay? Looks like that third column goes extinct pretty fast, doesn't it? What does that third column represent? Oh, it looks like I drive the resource down to nothing. That seems a bit odd, doesn't it? It seems unlikely to be the case. Maybe. Entirely baffling?